everyone. So today we will hear a talk from Siddharth, and he's a PhD student in Christian Andersen's lab. And so today he's going to talk about fluxoniums, which are, in my opinion, they're much less popular than transmons, and I think they should receive way more attention. And so first he will give us some overview and then talk about fabrication of fluxoniums, coupling them via a transmon and improving the gate fidelity. So the floor is yours.
Thank you. So hi everyone, I'm Siddharth. Today I will talk about building quantum computers with fluxoniums. So I was thinking about the title when Julia asked me about the title. And I thought of this because this puts the work I have done in the past 4 years in the lab in the broader context of building systems, which eventually might become quantum computers. So let's start. So for the talk, I will basically go through some basics of quantum computing with superconducting qubits. Then I will talk about circuits and fluxoniums mainly. Then fabrication of these qubits. Then once I've covered that, I'll talk about the 2-qubit gate scheme, how to do pulse shaping for these gates, and finally, what are the performance of these 2-qubit gates. So let's start. So when we think about quantum computing, we need the basic unit for the quantum computing is a qubit, which has a two-state system. And this is basically 0 and 1 represented on a block sphere, which you can use to encode your information. And this is a representation of the qubit, but this is let's say, a physical qubit to start with. The physical qubit is basically an implementation of qubit on a certain physical system. It can be ion traps, it can be superconducting qubits, it can be spin qubits. When you try to implement it on a system, you are prone to error because you are going to have interactions with the environment, and those interactions will lead to some decoherence and some errors. So people came up with the idea of encoding logical qubit, which is what you can use to do quantum circuits on multiple physical qubits. What I mean by that is you can use a lot of physical qubits. In this case, it's rubidium atoms, let's say. And then you can make an entangled state of all of these to make a logical qubit. What happens is if you have an error on one physical qubit, you can correct for it, but the state of logical qubit can still be preserved. And that logical qubit can be used to do a quantum circuit. Now, this idea is called quantum error correction, and there are various ways through which you can do quantum error correction. Specifically on superconducting qubits, we use a variation of quantum error correction called surface code. And in surface code, what you do is you take a bunch of qubits and you encode your logical qubit there, and then more number of qubits you have physically, the better your logical qubit can detect errors and you can correct for them. So you can go from, like, here 3 cross 3 is the number of the yellow points, which are the data qubits, and the red ones are the ancilla qubits, which are there to detect the errors. So this is the idea of quantum error correction. In superconducting qubits, there has been a lot of progress in implementation of these. And to show you some recent progress, Google came up with their recent results in the second half of 2024, where they made these logical qubits using big collection of these physical qubits. So here is a graph from their paper where they show logical error probability on the y-axis, and then quantum error correction cycle on the x-axis, which is a representation of time. So as you go more forward in time, you basically increase the errors on the system. And let's say your logical qubit is encoded in the 3 cross 3 system, you basically increase the errors as you go ahead in time. And then this green dotted line, which is the physical qubit, is basically your error of the physical qubit if it was used. And then you see the 5 cross 5 and the 7 cross 7 cross the line of physical qubit. This means your logical qubit starts performing better than your physical qubit. And this is a very important demonstration last year, because this tells you that if you keep increasing the number of physical qubits, your logical qubit gets more robust. Another interesting thing to see uh, is this black line, which is written as sycamore. So this is a previous processor they had, and there the physical qubits had slightly less T1, T2 times, the decoherence times. And because of that, the logical error probability increased even for less number of error correction cycles. So this means there are two ways you can improve the performance. One is by increasing the number of your physical qubits, and the other is by improving your by increasing the performance of an individual physical qubit. So we would be considering fluxoniums in the light of improving the individual physical qubit. And as we scale those systems, probably we would get better performance of the logical qubits. So one can ask, why do we want to implement this using superconducting qubits? So there are a few good reasons. One is that when you have this circuitry of the control lines reading out, sending your signals and interacting with your chip, you want low dissipation. You do not want dissipation. And this is a necessary condition. So low dissipation happens on these superconducting qubits. Second is you are able to get nonlinear, non-dissipative elements, which you need to create some nonlinearity in the circuit. And I will show why this nonlinearity is important. The circuit design within this arena of superconducting qubits is very flexible. It allows you to make different kinds of qubits, and you can play around with numbers to create slightly different variations. And that allows you to make a chip where you can think of architecture and place your qubits accordingly. Fourth is precise control electronics. So what has happened in the classical domain is recent years we have gotten better at microwave electronics, which is allowed us to do single photon level control. And finally, these processes, the chips, the fabrication processes which we use to make these chips are compatible with the current tools and use silicon and sapphire related technologies. So that's also good. So, okay, now how do we make a superconducting qubit? We basically use a few simple components, and those can be laid out like a simple electrical circuit. And the components here are the capacitor. So a capacitor with a capacitive energy EC, a simple inductor with a inductive energy EL, and then finally a nonlinear element Josephson junction, which uses the Josephson effect and has a characteristic energy of EJ depending on the phase phi, which is the phase across the junction. But each of these components have their own channels of errors. So common sources of error for a capacitor is basically having some stray charges on the capacitive plates. For an inductor, it could be some magnetic fields in the environment, so having some flux noise. And finally, for a junction, since you make a junction using a sandwich of aluminum oxide, aluminum, where aluminum is the superconductor, aluminum oxide is the insulator, and this leads to the Josephson effect. But within the oxide barrier, there can be material defects and impurities, which can lead to some two-level systems. And once you apply fields within these circuits, they can start absorbing energy, and this can lead to losses. So keeping this in mind, this is just the components. Now we need to build circuits out of it. So to build circuits, we start with a simple circuit of a harmonic oscillator. So we take one capacitor with one inductor, and with this, basically, if we apply some phase across the circuit, we will get harmonic oscillator. And when you are in the quantum regime, you will get a quantum harmonic oscillator. So when you solve the Hamiltonian, it looks like this, where your energy in the scale of h omega r, where omega r is the resonance frequency of the circuit, is on the y-axis. X-axis, we have the superconducting phase. And your energy levels are separated from each other by a gap of h bar omega r. So you can see the energy levels goes from 0, 1, 2, and so on. Each energy level is separated by the same amount of energy. So we have made a good quantum system here, but the problem is that we we cannot address the individual levels here. So what I mean is, if you want to excite your system, let's say from 0 to 1 or from 3 to 4, or you want to have this ability to control individual excitations, you cannot do that because all the levels have the same difference. So whenever you are sending a packet of energy, it will end up exciting to the next level. So for this, we introduce a nonlinearity, and that is the idea of a transmon, where you put the junction in the circuit instead of the inductor, and the inductor acts as a nonlinear circuit. What you get is a potential which looks similar to the quantum harmonic oscillator, but is slightly different in the sense that your energies now are not same, but reducing as you go up in terms of energy levels. So your difference from 0 to 1 is omega 0, 1, from 1 to 2 is omega 1, 2. And now we have the ability to say, okay, I only send the omega 0, 1 frequency, and then it will excite from 0 to 1 and not from 1 to 2. So we have the possibility to control the system at the individual levels. So that's a good thing. And that's why we can use this system as a qubit. And when I say use this system as a qubit, I'm only using the first two energy levels as the system, and the rest still exist, but we are not considering them for the qubit. And the first two, 0 and 1, are called the computational subspace. And this is what will comprise our qubit. You can make higher level systems with transmon as well, but I will not talk about them here. So we have made a good two-level system, but there are obviously some drawbacks. So the difference between omega 0, 1 and omega 1, 2 is called anharmonicity. And when you are sending the microwave signals, the signals always have a spread in the frequency domain. So let's say when you start sending a lot of power to your qubit, what will end up happening is there will be excitation happening between 0 and 1, but there will also be some amount of leakage going to the second level. So your system will go from 0 to 1, but also there will be some population which can go to the second level. And this is basically termed as leakage. And this is one of the problems in transmon. And that is where the idea of fluxonium comes in, to improve this nonlinearity and sort of push the levels away further. So what I mean is, your 0 and 1 levels are close to each other, but the difference between 1 and 2 is higher. So what you are doing is you are creating more anharmonicity. The 0 ground state is generally the symmetric superposition of the clockwise and anti-clockwise current flowing in the loop here in the circuit. And the 1 level is the anti-symmetric superposition of the clockwise and anti-clockwise current flowing in the loop. You can say that now you have introduced 3 channels. This can lead to more losses because you have introduced more channels or more sources of loss. But at the same time, the frequency difference between 0 and 1 is different from the transmon. In transmon, this is generally few gigahertz, generally between 4 to 8 gigahertz. In case of fluxonium, you can make it all the way from a few megahertz to a few hundred megahertz. In our case, when I will talk in my um, in my 2-qubit gate implementation, our qubits are around 100 megahertz. So good, now we know the idea of fluxonium, we know how the levels look. So how do we physically realize a fluxonium? So first we will have a look at the capacitor. You can have a planar capacitor where you will have some electromagnetic field distribution due to the capacitance. Then for the junction, you need to take advantage of the Josephson effect. So you create aluminum oxide barrier and aluminum here. And when the Cooper pairs tunnel through this barrier, you get your characteristic Josephson energy. Finally, to create an inductor, you can say, uh, I want to use a long wire, just like classical inductor. But the problem with placing a long wire on the chip is it's very hard to put a very long wire on the chip. And secondly, if you start putting a long wire, then it will have some self-capacitance. So you will end up with increasing like you will not get the right value of impedance. So what we do instead is we use the effect of the Josephson effect to create a linear inductor by placing a lot of Josephson junctions in series. And once you make it long enough, it starts to become linear. And this is what we use as inductor in the circuit. So now we know how we can try to realize a fluxonium in terms of components. So let's start to fabricate these qubits. For the fabrication, generally these superconducting qubits, you need a substrate which can allow you to have very low losses. So high resistivity silicon or sapphire, they generally have loss tangents which are 10 to the power minus 7 to 10 to the power minus 9. And then on top of that, you want to put your superconducting metal, and this metal should not have very lossy oxides. So that is how you try to decide which metal I want to put on the top of the substrate. In our case, we put two different kinds of materials which we have experimented with. One is the niobium titanium nitride. This is a alloy, and tantalum, which is a elemental superconductor. And then the choice of substrate has been silicon and sapphire. So we experimented with different combinations, and the most used combination is niobium tinitride on silicon. And we deposit it using physical vapor deposition techniques like magnetron sputtering. Uh, yes, so this is the first step which you define your metal. Then second, you use electron beam lithography or optical lithography. And then you define your pattern in the resist. You develop it, and that's how you get your pattern. And then in the next step, you want to convert that pattern into the lateral features on the metallic layer. So what you do is you put it either in wet etching solution, or you can use reactive ion etching, in which the plasma bombards your chip and removes the material in a directional way. In our case, we use a combination of SF6 and oxygen to do a directional etching. And this is how our features are on the chip now. Next, we need to create Josephson junction on our chip, which we will use for the junction. Um, so what we want to do is we want to have a superconductor, an insulator in between, and a superconductor. And you cannot have galvanic connection across the insulator. Otherwise, the tunneling will not happen. So what you do is you use a technique called double angle evaporation, where you define two channels like this blue channel and this red channel here. And then you do an angled deposition in such a way that your electron beam the electron beam evaporation, the aluminum is coming from the source, and it comes first in the first direction, and then you rotate then you expose it to oxygen so that you can grow a nice and thin aluminum oxide insulator. and then you rotate the sample in the right configuration, and you will get the second electrode. And this is how you are creating your barrier here. So you can see this is the sandwich, and at this side you can see there is no galvanic connection between these two electrodes, and that's important. Okay, and so to show you how the images look like, actually, this is the image of the metallic layer here. This is for scale. This is the qubit is roughly 400 micron across, and this pocket itself in silicon is 1 millimeter. These two are the capacitor plates, the yellow pads. The green line is the flux line, which provides the magnetic field. The blue part on top is the readout resonator. And then at the bottom, we have the charge line, which will give us the excitation, which allows us to excite the qubit. If we zoom in into this region, we have our metallic uh, uh, plane, and then we have the inductor here connected with a chain of Josephson junctions. And then in the middle, we have one single junction. If we zoom into this further, you will see that this is the junction. And this is relatively a big junction of roughly 250 nanometer by 250. We go up to the size of 100 nanometer by 100 nanometer. And at that point, it becomes difficult to control the dimensions precisely with lithography. Questions till now? Okay. Questions. So this is good, but what are the difficulties in fabrication? What are the problems? So here is a image from, yeah.
Sorry, question about the previous slide. So the chain of junctions here is different than typically used to see. I guess you can arrange the junctions in a number of ways. Is there a reason you chose for this zigzag pattern?
Yeah. So what happens is, well, the answer comes in the further slides, but what happens is you have to define the junction with some clearance for the resist itself. But this clearance, if it's too big, then the resist can collapse. At the same time, two of these clearances, if they are close to each other, you are cutting into the resist, and the resist can collapse like this. So what I try to optimize for is basically making sure that the resist is sturdy enough in all locations. Otherwise, I could have just created like a ladder kind of structure, but there the clearances were not enough. So I had to make sure that the perimeter is uh, the smallest as possible. And secondly, the area of this loop is also small, because those two factors contribute to the flux noise in the system. And that's why this was sort of the optimal geometry, which I could reach. Probably we can maybe, so at the moment I'm working on trying to optimize it further if I can. So coming back to the difficulty in fabrication of these junctions, what happens is when you deposit a layer by layer aluminum, let's say in this case, your oxide can also grow like in a layer by layer fashion. And then your aluminum on top also grows in a very crystalline way. So your interface is very clean. Your interface is going from a crystal to another crystal, and then on top another crystal. But with the method which we are using, which is the electron beam evaporation, your aluminum atoms are not coming in a layered manner. What happens is more like this. You are getting chunks of aluminum flying onto the chip, and then the the boundaries between different aluminum portions are like not very crystalline, and your oxide growth is very amorphous. And the thickness of the oxide is also varying across the whole thing. What this does is basically, when you have a superconducting phase in your material, your Cooper pairs will tunnel through the minimum sort of the barrier, because that is the point where your Cooper pairs tunnel through. And yeah, this becomes a problem when you think about putting two of these junctions next to each other you cannot have a very consistent reproducibility over first the junctions and then across chips. So those are some difficulties which we face. Next, so these were some initial junctions which I'm showing from all the way from 2022. You can see the surface on which the aluminum is coming first is already very rough. Secondly, there is some dirt on the side of the junctions. Also in this picture is visible is there's some black polymer like stuff which is underneath the junctions. And this is what made the reproducibility even harder. And I tried to solve these problems. So with a lot of help from different people and Anand and Mathve especially, what I was able to do was improve the junction quality over time. What I did was do a two-layer stack where I can deposit the aluminium like this with some clearance of the resist away from it so that the resist after development does not come underneath the junction. And here is a SEM image of this resist stack, how it looks like in a cross section. So that is from Nandini's paper, which is cited here. And this is what we made. And we went from these initial junctions, which we had back in 2020, to the current junctions, which look way smoother, are much more, the targeting is better in terms of the EJ values, which we need. And these are current junctions from 2024, 25 now. So now we have realized the fluxonium. You got your single qubit defined on the metal plane, you get your junction, and then you also get your chain of the junctions. So now coming back to the original question of making a physical system for quantum computing, first is the realization of physical qubits, and we were able to do this with in the lab with Figen's project initially, and then we demonstrated we can make fluxoniums. Second goal is to do control of these systems and do single qubit gates. And with Martine, we were able to show 99.96% fidelity for these gates at 20 nanosecond gate time. So that's a pretty good performance. The next step is to do a 2-qubit gate for these kind of devices. And me and Eugene worked on this project, and we got a 99% fidelity for 60 nanosecond gate. And finally, you want to read out the state of these qubits. And with recent theoretical proposal from Jinlun and the experimental demonstration from Taran, we have shown that we can also read out using fluxonium. So all the steps which you need to do towards a quantum computing system, we have slowly realized these 4 or 5 requirements in the past 4 years. So now I will talk further about the project. So I just built up to this point to show you a single fluxonium. Now we will talk about 2-qubit gates on these devices. So, okay, now you have your single fluxonium. That's good. But now to do a 2-qubit gate, you want to have 2 fluxoniums and do interaction between the 2 of them. And the question is, how do you do that? Can you put them close to each other, couple them in a capacitive manner, or do you connect a wire between them and couple them in an inductive manner? But we want to avoid the constantly on coupling, which happens if you put them too close to each other, because these always on coupling, in the field they are referred to as ZZ coupling, they can lead to buildup of error, and that slows down the gate time. So we chose to do this with a transmon in between. Now, why transmon? Because transmon frequency is in a few gigahertz, and the fluxonium frequencies are in a few hundred megahertz, let's say. So this is how we will do a 2-qubit gate using a transpon in between. And this is what the device looks like. Here you see 2 fluxoniums in blue, 1 transpon in between in the green. Then each of these qubits have a flux line here in purple. This flux line is basically used to bias the qubits at the right frequency spot. We also have the readout resonators. We only put 2 readout resonators for the fluxoniums, and we have 2 charge lines for the fluxoniums. Now, when you come to a 2-qubit gate, the question is, what do we want to optimize for? We want to optimize to have low crosstalk between qubits because you are going to increase the number of qubits now. Here we aim that both the fluxoniums have less direct coupling between each other. Second is the fidelities. So fidelities are the parameter which you use to assess the performance of the gate, and we want high fidelities, meaning good gates. We want faster gates because when you have a qubit, it will eventually lose its state and decohere. And you want to make sure that before losing the state of the qubit, you can do as many gates. So that's why the requirement of doing faster gates. And finally, pulse shapes, simple pulse shapes. Why? Because the optimization of the pulse shapes can take a lot of resources, both numerically and also in experiments. And I will come back to this further in the presentation. And that's why we use this architecture where we have fluxoniums coupled with a transmon. So this is the gate which we want to do. This is a CZ gate where your control qubit is A, the target qubit is B. If A is in 1, you should be able to do a minus sign, and the matrix looks like this. How do we do this? We use 2 fluxoniums, the states of which are 0 and 1. So when you combine the system, it will be 0, 0, first qubit in 1, second qubit in 1, and both the qubits in 1. And this will constitute our computational subspace. All these 4 levels will be below 1 gigahertz. And now, if you think that the coupler, if you think about the coupler, it's also within the system, but it's not being used directly for the gate. The states are encoded on the fluxoniums itself. So the coupler is G, which is the ground state. And when you think about the excitation of the coupler can go from the ground state to the excited state. So all these 4 levels have, let's say, the same transition of the coupler from ground to excited state. Ideally, the frequencies would be same, but since the fluxoniums also have the higher levels, the repulsions between those levels and these levels lead to slight differences between the 4 frequencies. And another thing is these levels are close to 5 gigahertz. So the fluxonium levels are well isolated here compared to the coupler levels. So what you want to do is you want to do a Rabi cycle by picking the 1-1 state, go to excited state, come back, and this will induce a phase of 2 pi, this will develop a phase of pi, and this will lead to a -1 sign like this. We do a Rabi excitation based on which states the fluxonium start in. So to show experimentally, we started with seeing the spectroscopy of the coupler. Here on the y-axis, we have the readout signal to see the state of the qubits. And on the x-axis, we have the drive frequency. So we are driving the coupler at a particular frequency, and we are trying to see where the coupler is. So this readout signal is for the coupler. We see 4 peaks corresponding to 0, 0, 0, 1, 1, 0, and 1, 1. These are the 4 states of the possible states of the 2 fluxoniums. And we only want to drive this particular transition, and we don't want to drive these 3 transitions. This is a nice Rabi oscillation if you can drive exactly at that frequency. So on the y-axis is the signal to see the Rabi oscillation, and the pulse amplitude on the x-axis. And you see for 40 nanosecond pulse, you only see a Rabi for the 1-1 state and not for the other states if you pick the right frequency. And this is how you will get a CZ gate. Okay, now given this, there is a small problem. So, yes.
It's 40 nanoseconds for to complete the
I will show the results of the fidelities for versus gate time in slides next to it. Uh, let's take a slight detour of the pulses which you are sending to the coupler to excite the system. What happens is you use like you can continuously excite the system from your 0 to 1 state, but then you will basically be always either in excited state. So to avoid that, you always send pulses of small pulses of excitation. So here we have a carrier frequency of omega, which is your omega 01, but then you put it in a control envelope, and this control envelope will basically the length of this control envelope gives you the gate time in which you are going from the state 0 to 1. The problem is when you have this kind of envelope, in this case, this is a Gaussian envelope. The envelope will have a spread across time and frequency. So on top in the B figure, you have the Gaussian pulse for 1, 2, and 5 nanoseconds. And in the C figure, you have the Fourier transform of this figure where you have the frequency on the x-axis. And you see the shorter the pulse, the more spread out it is in the frequency domain. This means that if there was another level, which is E2, and the difference between this excitation and this excitation is alpha, and the spread is bigger than alpha, then you will end up driving E2. So you do not want to drive E2. And that is a requirement to avoid leakage. So what happens is the shorter the pulses, the bigger the spread and more the leakage. And this is why the gates become slower. This is only one level. What if you had 4 levels, like in our case? Then it becomes even more tricky, and then you need better pulse engineering to control the leakages into other states.
It doesn't become more tricky because as you see with a Gaussian, if you just center it around the 1, you would be limited by the overlap of the bandwidth with the 1, 0 state. And the other ones would be even more suppressed because you're just further away.
Yeah, but if you look at the curve here, this is for 1, 2, and 5 nanosecond, and this corresponds to the frequencies already 250 megahertz here. But in our case, the spread is, let's say the first spread is a difference of 50 megahertz, then less than 50 megahertz, and then the overall span is 150 megahertz. So we do not have a big frequency span to play with. So our the leakage starts happening around 24 nanosecond, 30 nanosecond is where we see already the errors have gone very high.
Okay, but that's still very fast to keep get, right?
Yeah, like we can always go faster. So like 50 nanoseconds is already fast enough, but then globally, I think Google has demonstrated, I think sub 20 nanosecond gates. I'm not sure with what fidelity.
And before you said 2-qubit gates that you made around this schema was 60 nanoseconds.
Yeah, so that's to hit the 99% fidelity number. Okay, so we started with thinking about simple pulse shapes to start with. We chose cosine pulse envelope where the amplitude looks like this, going from 0 to the gate time Tg. And this is what the performance looks like, where you have the error of the gate on the y-axis and the gate time increasing on the x-axis. Generally, what happens is as you decrease the gate time because of more leakage, the errors goes up. And as you increase the gate times, the error comes down. But at some point, your qubit decoherence kicks in, and then the error starts increasing again. So this is like a general trend which you see in superconducting qubits. 99% has been dotted as the fidelity, or the threshold requirement to do quantum error correction is you want to have 99% fidelity to be able to make your logical qubit better than the physical qubits. and this is the number which we want to hit. And with the cost envelope, we see this. Now, if this is the simulation, and the measurements follow the simulations closely. There is a spread accounting for the system parameters uncertainty. Now, if I zoom into the 32 nanosecond point, you see the spectrum. Remember, this is a spectrum of the Fourier spectrum of the cos pulse, so it doesn't look exactly the same as cos. So you see dips, but the fold transitions are F11, F10, 01, and 00, and we only want to drive the 11. But at the same time, you see a good amplitude also present at 10. So that is the main cause we are seeing this kind of performance here, where we max out around 64 nanosecond. Next, we tried a cost drag pulse. What in cost drag, what you do is you introduce another control envelope called quadrature envelope here. And with the mixing of these two, you are able to kill out transitions at a few frequencies. And in this case, you can see that at F10, we do reduce the amount of frequency component present here, while at F01 and 00, we are still relatively the same. And you can see the improvement in performance with these green dots. I hope it's visible with the projector. Okay. And we see that for even shorter gate times, we are able to go close to 99%. And this is exactly at 60 nanoseconds that we get 99%. So we are able to cross that. And we were looking into how can we improve the performance from here. And this is where fast track comes in. This was a technique demonstrated previously on single qubit gates, and we wanted to test it on 2-qubit gates. And what this does is it shapes the pulse using a Fourier series sum, both for I and Q. And you can see we were able to broaden the window of suppression for F10 here. And it is similar sort of a performance at F01, but at F00, we have increased the frequency component. But at F11, we are still the same. So what happens is when you decrease these components, you are spending less time in the transmon state and more time in the fluxoniums. If I show the difference between these three, is the first is the cosine pulse envelope, second is the cost drag, and the last one is the fast drag. And you can see for fast drag, the performance comes close to or better than the cost drag at the shortest gate time. And then it remains closer to the 99% fidelity. So this means the fast track broadly is able to maintain the performance of fidelity close to 99% for a broader set of gate durations compared to both cost drag and cost. Although the global number for like the best fidelity is still 99%, and maybe we can fine tune and figure out whether we can improve. So this was the result which we recently put on archive. And then if somebody wants to scan the QR code to see the paper, they can do so. Okay, he's taking out the phone, but I'll go.
You've mentioned at some point the qubit is imposing a limit, the coherence of the qubit is imposing a limit on the performance of the secret. Is it the qubit or the coupler?
So here it's the coupler. I think in the regime where it's going up, it's the coupler. Here, yeah, here it's like a good question. What is exactly the limit of?
I'm guessing for shorter gates, it's more likely that you will be exciting the other peaks. Let's say, isn't something that have you measured or seen the residual population of the coupler? Let's say, if there's anything.
No, we didn't measure that. So our coupler here has a T1 time of 1.2 microseconds roughly. So it's not the best, but this has allowed us to do this kind of gate. Probably the improvements can be made both in the decoherence time and also execution of the pulse and seeing where the population exactly is. But okay, to summarize the talk, I'm also almost done with the time. So first we understood sort of what are the requirements to do quantum error correction, then what are fluxoniums, finally how do we fabricate these fluxoniums, how to do two-qubit gate with a fluxonium. Then we had a look at simple pulse shaping to do these kind of gates. And we were able to show good fidelities with these two-qubit gates of roughly 99%. And with this, I would like to thank my team.
Okay, so I didn't see any questions online yet, only rather comments than questions. So then who has questions?
Hi, thanks for the talk. It was pretty cool. I was just wondering, what are the yield of your devices? Like, so, and what's the bottleneck within the fabrication time? Because it seems like the inductor that you make with all the just fragile.
Yeah, so let me go back to the. Okay. So you can see here that first thing is the placement of these levels. The placement of these levels depend on the energies of these individual qubits because you are using inductor, capacitor, and the junction to make individual qubits. So what's critical is that you are able to target all three close to the values which you want in a way that these four levels are still far apart from each other. So the yield is good, but the targeting is what becomes critical here. And sometimes you are unable to get the right targeting, the levels are too close, or you are unable to see the levels, and sometimes one qubit is not working. So then it becomes a question of can you get the right targeting with what you have fabricated.
On chip of approximately how many devices?
So we used to put 4 sets of these on each chip, and sometimes like not all the sets are working on the same chip, so you would get like 1 or 2 working sets, and within those sets sometimes the coupler is exactly close to the resonator, so your leakage is high. And I think it took us 6 of those chips before we could come close to the exact numbers.
Okay, so anyone else? Okay, so just then my curiosity questions. Maybe you mentioned, but I didn't see like the T1s of actually the two. So for the coupler transmon, it's around microseconds, you said, right?
Yeah, I should have
This
put
is
that.
mostly because it's tunable, right? Like it's because I mean, as for transmon, it could be way better. So it's
So yeah, there are multiple reasons for a low T1 because our fluxoniums on the same device have shown 50 microseconds and beyond T1 within the same set. So the question, we are also trying to understand better what is the exact reason. It could be the junctions placed in this particular geometry has this kind of T1, or we also have the placement of the resonator close to the qubit, so it's also not allowing us with the best T1 of the transmon. So it's a combination of factors.
also
I
it's
cannot.
not, maybe it's not even the dielectric losses that typically limit the transmon.
So that is part of the answer, but
Okay.
what exactly is the main limiting factor? I cannot really pinpoint.
Sorry, and so you said for Fluxonia, it's how many microseconds you said?
So it varies from chip to chip, and I don't remember the exact numbers, but for them, I think they have like 70 microsecond T1,
Ah, okay.
and T2 is around 30 to 40. I don't remember the numbers from top of my head.
Okay, and just another question. So here you do like Rabi, so you do pi Rabi pulse, right? So you're populating a level in the transmon, not virtually, but actually
Yeah, you are
real
just
population, right? So it means that T1 of the transmon limits your
So you do not want to spend too much time in the transmon one
right.
state.
Yes, but so some schemes where you have, let's say, I don't know, something Raman like where you're not populating it actually, but virtually. So then is this that the coupling strength is too small, or what is the reason?
I
For
don't
this
know.
specific coupling.
I haven't thought about that, and I don't know exactly how that can work in this particular configuration. But yeah, I can have a look later.
Okay, okay. Sorry, and last curiosity
Yeah,
question.
sure.
I'm a Fluxonium fan, so yes, I just a curiosity question. So your ELs, you also didn't see the numbers. What are the EL values in your devices? It's not very high inductance, right?
Yeah. So this is like in terms of gigahertz or in terms
Yeah,
of.
gigahertz. Yeah.
So I think both of these had like 0.6 gigahertz. So not very. I don't know how that's high or low.
Okay,
Depends
so
on
I
what
mean,
you are comparing to.
Okay, so then compared to the plasma frequency, then I guess it's
Compared to the plasma frequency, yes, probably the plasma frequency of the inductor itself is above 10 gigahertz. Uh, but probably above 12 gigahertz even. I don't remember the number.
yeah, okay. Yeah, thanks. So yeah, thanks a lot for the super clear and nice talk. Yeah, it was
Thank you.
very nice.
Any more
And
questions?
yeah, so if there are no more questions, then we are okay.
Since talking coherences, in transmons we typically and transmon with tunable couplers, we typically see the coherence of the qubits depend quite a bit as we change the frequency of the couplers. Is that something that you see here? You say that your coupler is 1 gigahertz, 1 microsecond, and
Yeah, on one of the samples we did see when we were shifting the coupler between different points.
It's not keeping the coupler at the hard flux quantum, I guess. Would you see a dependency on the coherence of the coupler as a function of coupler frequency?
Yeah, we did see this kind of effect on one chip, but we didn't do thorough experiments to say, okay, yeah, it is this kind of relation. And so we measured at two spots only, two flux points. And then we were like, okay, we see a better T1, T2 here at this point, and that's the point we chose to do the gate. But why exactly the T1, T2 are decreasing at that point, that I cannot really.
So you choose the bias of the coupler to maximize the coherence of the qubits.
Yes.
Okay.
And also the transpon itself.
Okay. Because I'm used to seeing that the usually is the coupling, you choose the bias position, the point at which you are canceling the coupling between the.
So in our case, the coupling is already very low. So the direct coupling between F1, the fluxonium 1 and 2 is like 19 hertz. So if you mean the ZZ coupling, it's very low already. So we are not really concerned about the ZZ coupling, but we are thinking about how do we get these 4 levels in such a way that we can drive the 1-1 the best and not the other levels so much. So yeah, it's a combination of where we get good coherence times and where we can place these frequencies to optimize the gate performance.
It's a bit of a mystery to me. Why does it depend? In the case of transmons, I think I understand, but for fluxoniums, I don't fully understand why would it depend on transmon frequency.
I think at some point we had this discussion, should we do more experiments? But yeah, it is like a separate study in figuring out how does the coherences depend exactly on these dependency of the coupler and the fluxonium.
Okay, cool. So then let's conclude. Let's thank Siddharth again.